The Circles Project is an intercontinental cross-institutional collaboration that aims to dampen waves in traffic flow called phantom jams. If you have ever encountered a temporary stop-and-go traffic jam for no apparent reason, this might have been a phantom jam that occurred naturally because of human driving behavior. These oscillations are generated by traffic instabilities, which cause significant variability in vehicle speed, leading to increases in energy consumption and decreased safety. Prior work on closed-course testing has demonstrated that phantom jams can be reduced using autonomous vehicle technologies and specially designed control algorithms. The Circles project seeks to extend this technology to real-world settings where reducing these negative traffic effects could provide over 10% energy savings by using only 5% of the vehicles on the road to pacify traffic. With a small number of Level 2 enabled cabs, we will demonstrate the ability to improve global energy efficiency of the entire traffic stream. Our team, ironically empowered by the COVID-19 pandemic, features multiple highly collaborative and cross-functional subteams, from microsimulation of traffic dynamics to physical vehicle deployment, from mathematically optimal vehicle controllers to AI-trained control policies, and from computer vision tracking of a highway corridor to vehicle energy modeling. Each subteam helps piece together a complete migration pipeline. First, we will hear from our wave calibration team, our most eclectic team, consisting of members from 4 universities. The team works on modeling the flow of traffic, ensuring that we have microsimulations that accurately depict phantom jams.
Phantom traffic jams seemingly occur without a cause, but are in fact due to the way that humans drive. When roads are sufficiently crowded, small deviations from smooth traffic can grow into phantom traffic jams, which ultimately leads to stop-and-go traffic. These jams waste time and energy and are a common, frustrating experience for many commuters. A goal of our work has been to extend the open-source traffic simulation software, known as Sumo, such that it can produce these phantom traffic jams and match our field observations. It is essential to be able to simulate these features of traffic accurately so that we can design our control algorithms to eliminate them.
Next, the energy team, operating at the cross-section of applied mathematics and engineering, builds the models by which we evaluate energy improvements and, spoiler alert, reward our reinforcement learning agents.
To quantify the energy improvements, both in simulation and in actual road tests, a hierarchy of vehicle energy models is developed that accurately capture the impact of driving under strong non-equilibrium flow conditions, yet are structurally simple and generalizable. The Circles team is using the highly accurate and complex vehicle energy software Autonomy, which is developed by the Argonne National Laboratory on behalf of the US Department of Energy, and is developing systematic model reduction techniques to derive a hierarchy of simplified models. The model reduction pipeline exposes the Autonomy energy models to a virtual chassis dynamometer that works just like a physical vehicle testbed. The dynamometer exposes the vehicle to a full parameter space of possible driving conditions, and thus yields accurate energy metrics for highly unsteady driving. The energy models are then combined with traffic models that reproduce realistic traffic waves.
Next, we will hear from our hardware team on how vehicles are being prepared for sensing and actuation, with an emphasis on scalability up to a 100-car CAV demo.
We have to look beyond using the single vehicle from small-scale experiments and start thinking at a much larger scale. How might we take 100 vehicles that we can control and do that without a monumental cost to actuate all of those vehicles? The way we're doing it is that we're going to be using available commercial vehicles as controllers for optimizing the traffic flow by plugging in our low-cost computers into those vehicles. This allows us to actuate the vehicles at a very low cost, taking advantage of the existing networking and sensing that's found in today's vehicles straight off the production line. In addition, we can also gather data from those vehicles in their everyday use in order to train and validate the controllers that we might be using. This allows us to check wave dampening cruise controllers that we're planning to deploy against human driving to make sure that we don't put together a controller that would be unlikely to drive like a human.
Speaking of controllers, the next 2 teams we will hear from are taking 2 vastly different approaches of designing vehicle controllers. The first team is using mathematics to derive an optimal vehicle controller.
The control algorithms are designed using mathematical models at different scales, including microscopic, mean field, macroscopic, and also multiscale. At the microscopic level, we combine traditional follow-the-leader and optimal velocity models, as well as consider the intelligent driver models. At the mesoscopic and mean-field level, we pass to delimiting the number of cars, obtaining coupled equations for the control cars and measures, which are a mathematical generalizations of functions, empirically interpretable also at the microscopic level. Finally, macroscopic and multiscale models are obtained by coupling partial differential equations representing wave dynamics with ordinate differential equations for the autonomous vehicles. The control algorithms are designed in a hierarchical manner, combining safety control, Lyapunov functions, PID controls, and hysteresis.
This next team employs deep reinforcement learning to train controllers. This team utilizes the energy team's models in their reward function and exposes the agents to various curricula to build robust controllers.
Learning in large, many-agent systems pushes the limits of multi-agent reinforcement learning algorithms. While these algorithms have achieved superhuman performance in board games and video games, the complexity of traffic systems poses a new set of challenges. Traffic systems contain many more agents than these algorithms are often designed for or tested on, and require the controllers to be both safe and robust. We started by testing and tuning our approaches on small networks, exhaustively filtering through state-of-the-art algorithms to find suitable candidates for our problems, and along the way developing new ideas for how to scale to systems with so many agents. We gradually increased the complexity of the systems that we worked on, moving from single-lane to multi-lane highways. At the moment, our system is designing controllers for a 1-mile stretch of highway, containing almost 1,000 human drivers and over 100 reinforcement learning agents operating simultaneously.
Whether a controller is analytically optimized, hand-designed, or trained via deep reinforcement learning, it can be simulated in a traffic environment with Sumo via our team's framework, the Flow software package. Our team has built into Flow a data pipeline for the automatic and standardized evaluation of these controllers. Simulations can be uploaded to an S3 bucket in AWS, which triggers a series of SQL queries that post-process the data into various reporting metrics. We've also implemented a front-end leaderboard that can display these computed metrics. This tool allows anyone on the team to view all submitted controllers and objectively assess them across a range of predefined metrics. This assessment of controllers in a simulated environment facilitates building trust in the efficacy of our controllers before moving them onto the next phase, testing for safety and controls in preparation for migration to physical hardware. For the topic of migration, we'll hear from the hardware team again for controller policy transfer onto the vehicles.
After we develop these controllers, we do a significant amount of safety testing with software in the loop as well as hardware in the loop to validate that the controllers will still behave safely when we transition them from simulation to the cyber-physical system. By building this pipeline, it allows us to take field experiments directly into live traffic much earlier than we normally could.
Finally, our testbed development team is the last piece of the puzzle to pull off our field experiments in live traffic.
Because of the high cost of traditional camera-based traffic monitoring systems, it has remained very challenging for the research community to get good data on the features of these phantom traffic jams. In a partnership led by the Tennessee Department of Transportation, we are building a testbed known as I-24 Motion. Located near Nashville, I-24 Motion captures the paths of 150,000 vehicles a day that pass through I-24 on a daily basis. I-24 Motion is designed as a scientific instrument, consisting of 4K resolution video cameras mounted on tall poles that offer a continuous overhead field of view of the roadway. Multi-object tracking computer vision algorithms convert the video data into trajectories describing the position, velocity, and acceleration of each vehicle. This trajectory data is validated with high-fidelity vehicle data collected on our own instrumented vehicles. Because I-24 Motion captures the trajectories of all vehicles, it allows us to estimate the energy savings to overall traffic resulting from the deployment of our automated vehicles on the roadway.
As you have seen, this is a sprawling effort with high ambitions. Our multiple sub-teams consisting of over 50 members spanning 5 universities and 7 time zones are working hard to bring this all together for a medium-scale test in Nashville this summer, followed by a 100 cav full demo next summer. All of this is possible not because of individual components, but because of everything coming together through convergence research.